After discussing very specific. What's the rank of the there? Very important.
Okay, so good evening, everyone. Again, welcome to today's asset colloquium, which is going to be given by Mr. Sanjay Wandhekar. He is the Senior Director and head of the Division of HPC, High Performance Computing Technologies from C-DAC. Firstly, I would like to thank Jairam for proposing this talk. And it was very interesting to note today that C-DAC is working on a supercomputer system for recording or processing rather live the data from GMRT using a 1 petabyte system, 1 petaflop system. So that is very interesting development. I never knew that supercomputers are used sort of online data processing elements. Mostly they're used for backend processing. So it's very nice development, and happy to see that C-DAC and DIF are coming back again, getting into such a major milestone. So I'm sure, so you will hear a lot of interesting things under this title of Overview of National Supercomputing Mission, NSM it is called, and also emerging trends in architectures of these machines. I think that is the more important aspect of today's colloquium. To just say a few words about today's speaker, Sanjay Wandhekar, as I mentioned, is a Senior Director at C-DAC, and he's also currently heading the HPC Technologies Group. He has more than 30 years of management experience in developing and design of HPC systems, and also on the IPTV and OTT, as you know, which are in some way the disruptive technologies. Now everything, all entertainment has essentially moved on to these technologies. He studied electronics and communications, College of Engineering, Pune, and did his master's at IIT Kanpur. And he's currently heading the National Supercomputing Mission, as I said, activities at C-DAC, which mainly include establishment of supercomputing facilities as well as the ecosystem development in the country, and the development of critical HPC technologies like, this is the most important part of this mission, the compute servers, high-speed HPC interconnects, and also the system software stacks. Since for about 10 years, he and his team has established more than 30 such installations, facilities in the country. And for that, he and his team has received Dr. APJ Abdul Kalam HPC award for their contribution to supercomputing ecosystem in this country. Sanjay, of course, has proven track record of building, mentoring, motivating high-performance teams at C-DAC and also in the industry. He has, in fact, quite a comprehensive experience in all phases of product development, ranging concepts to production and also services. In fact, he was the lead member in the development of India's very first supercomputer, which you remember as Param 8000, and also all the subsequent Param series of supercomputers. I think we have a real technical expert in this area of supercomputer, And I think we are very much looking forward to their program.
Good evening, all. Am I audible at the back? So first of all, I would like to thank the for giving me this opportunity to talk to you regarding what we have done till now under National and explain about what are the trends and in the architectures of the HPC systems globally, and as well as what is basically our thought process on the these architectures which are coming up. So yeah. So brief about the National Supercomputing Mission. Here, this mission started way back in 2015. Basically, it approved in 2015. It started in 2016, and it is supported by two ministries, DSP and IT. And there are two implementing major agencies, C-DAC and Indian Institute of Science, Bangalore. So, there are four pillars of this mission. One is basically building the supercomputing infrastructure within the country. Second one is basically building the technologies which are required for building the supercomputer. Third one is basically application developments of national need. And fourth one is basically creating the manpower required for this managing and basically using this kind of systems. So till date, we have established about 15 facilities on this mission, which is having compute power of 24 petaflop. And we are planning to have another 40 petaflop in next 1.5 years timeline, and which will make it about 64 petaflop of compute power. So that is the plan under the building the supercomputing facilities within the country. These are basically getting established across the country. Second one is basically developing the various indigenous technologies, which includes servers, interconnect network, software ecosystem, and even the processor. So I'll explain about that in the next few slides. And I already told about developing the HPC applications. So 5 major areas the applications are getting developed. I'll not talk about that because that is again a separate longer session can be there on this application. So till now, 19,000 HPC aware manpower is actually developed under this mission, and the target is about 20,000. So basically, building this facilities, we have take the phased approach. So basically, idea was to have a completely indigenous supercomputer. So we started with assembly of the supercomputer within the country, where we use the components like motherboards, CPUs, and all those things. Started with that, assembled those things to make the system using our own software stack, which is based on open source. So that is the first phase. Second phase is basically manufacturing these motherboards within the country with the help of the industry partners. So there we build about mostly 13 systems, which is based on phase 2, which is manufactured within the country. Phase 3 is basically having our own design, and that is getting manufactured within the country. So that we are now entering into phase 3, and phase 1, phase 2 is completed. We have established 15 systems under phase 1, phase 2. So in phase 3, we are going to have 9 systems. One of them is at NCRA, as told just now, that is going to be a real-time system, unlike any other supercomputing system, where the data is coming online with 10 gig network, and that is getting processed and then getting stored in the storage. So there is no batch processing in that supercomputer. So these 9 systems of various sizes are there. One of the bigger system is going to be a 20 petaflop system, which is going to be a national FED. And that is going to be at C-DAC. Anybody can access that facility, and the 100% is to be used by the users across the country. So C-DAC will be just managing the system. So which will make the total compute power of 64 petaflops. So I think here I've just segregated this academic and commercial use, because some of the systems are possible to use commercially also, like whatever is going to be their national facilities, commercial means industry also can utilize. Even the R&D labs who can pay and get the priority on this system. So in case some important project is there, they want some priority, they can utilize this facility at some cost. Mostly the cost is basically for maintaining the system, having the basically electricity power and operational charges. So it is basically recovering those charges. So this is how it is actually segregated, this facility. So till now about 6,700 users are using these systems, and from 120 plus institutions, and 84 lakhs of supercomputing jobs are run on these systems by the users. So more than 500 plus PhD students are using these systems, and there are more than 800 publications these people have done using these systems. So these are the systems which are there across the country. So in last 4 years, we are established, started with 2019. Param Shiva is the first supercomputer which was done under this supercomputing mission. The largest one is at C-DAC, which is Param Siddhi AI. This is a GPU based system, and this is actually a 5.2 petaflop system. Now it is upgraded to 8.3 petaflop with another program called Iravat. That is again a different program of AI. These two computers are merged together into a single supercomputer, and that is 8 plus petaflop of sustained compute power. And that can be utilized for various AI loads as well as HPC loads. And other systems are at Param Pravega at ISC, that is 3.3 petaflop. Under phase 3, we are having 3 systems which are going to be large, 3.3 petaflop, and one of them is 20 petaflop. So as I told you, we are actually building the indigenous ecosystem, and we are developing various technologies to have completely indigenous supercomputer. So these technologies are starting with the basic processor itself. So we are building HPC processor, we call it OM. Then we are developing Rudra series of servers based on various architectures of CPUs. Then Trinatra is a scalable HPC network, because you need to connect all these servers together using a very high-speed network. So that is called HPC network. Then we have a system software stack which enables both HPC and AI workloads. Then storage is a very important part in any of these supercomputers. So we are developing a SSD flash-based storage, which is called DIOS. So this is going to be very high-speed storage, which will have very high operations per second. High operations per second. Another important technology which we are developing is cooling technology. So which is right now you can see there's a lot of any CPU is basically which is there in the current market. They are going to consume about 350 watts in one single socket. Now, how do you cool that? So you need a liquid cooling to cool this kind of CPUs. So we are developing some liquid cooling technology also with some partners.
Is it just water or some other liquid?
There are 2 types of liquid. One is water with some additive, and the second one is 2-phase liquid is also there. So that is again coming up the next way. But the concept is similar. You have that liquid going up to the CPU, and then the hot water will come, or the vapors will come out, and then that will get cooled by liquid heat exchangers outside this rack. That is how it is actually. I have one slide, maybe on that we can see, depending on time. So now with this Phase 1, phase 2 systems, we have got the experience of architecting and building bigger systems first, because that is another technology which we need to build the system from the off-the-shelf form. So that experience also is gained during this phase. So this is a development which is called, we call it Rudra server. This is under phase 3. We have developed this server. This is a very high dense server, half width, 1U form factor, where 2 CPUs are there, and also in 2U form factor, I can put 2 CPUs and 2 GPUs together. So with this, in single rack, I can have 64 servers or 32 servers with 2 GPUs each. So with this, about 35 kilowatt of power is there in one single rack. So that kind of compute power can be compressed into one single rack with this technology. Currently, it is based on second generation scalable processor, and this we are developing the next generation also. I will show you next slide. Now, this is completely benchmarked and validated with industry standard software stacks and applications and framework. And we support both NVIDIA and AMD GPUs. A100 is already validated on this. AMD GPUs also are the latest AMD GPUs. And we are actually productionizing about 6,000 Rudra servers for building the phase 3 systems. So this server will go in all the phase 3 systems, including NCR also, where in NCR case, most of the servers will have GPUs also. So that application requires a lot of GPUs. And we also have done the TOT to the industry so that they can make this server and then sell it to other markets and whatever we need. So basically, idea is to build the ecosystem of building the server within the country. So we are just trying to catalyze this so that the manufacturing industry comes up, then slowly the design industry also comes up, and then tomorrow some server vendor also will be coming up who can design and build and sell the servers. So this is a roadmap of our Rudra. Currently, we are manufacturing Rudra 1. Rudra 2 is getting built, which is going to be Sapphire Rapid, the next generation processor, which will also support Emerald Rapid CPU from Intel. And this can support 4 or 8 GPUs of various configurations from various vendors. Rudra 3 is going to be next generation Intel processor. And we are going to have our own processor called OM processor, which will be called as Ananta server, which will also have, again, GPU support. Depending on the application, we can have either CPU only machine or the GPU machine. So this is some kind of prototype of Rudra 2. You can see here, again, this is going to be a very high dense form factor. In one view, I have 2 servers. Each one is having, each CPU is basically 350 watt CPU. So you can see that in one view, you will have about 2 kilowatt of power. And that has to be dissipated. So again, we have to use liquid cooling. Otherwise, cooling one U with 2 kilowatt is not feasible in the current technology. Then we are going to have 4 GPUs again in the same form factor with one server each. So you can see here, there are 4 GPUs and there are 2 CPUs here. And all this is connected on the backplane for the power input. So this is going to be a 48-volt power supply, which is again central power supply. We call it as the open compute platform. This is again a standard where 48-volt power supply will be there and the rack, and through busbar, all the servers will get the power. Again, this is hot swap servers. You can remove any server at any time, depending on the requirement for any maintenance. So you can see it is. So here about 3.5 kilowatt power is going to be consumed when the GPUs are there. 4 GPUs are there. So it is again a challenging job to pull this kind of load within this form factor. And this platform will support the latest GPUs, which H100, then MI 250 and 210. Now 300 is also coming up. We are planning to support all these GPUs, including Intel GPU, which is going to come up. So next element which we are developing is the HPC network. Again, here there's a requirement of low latency and high bandwidth, and it has to scale to thousands of nodes. So we have come out with our own network, which is basically switchless network. We call it Trinetra, and this is a post adapter card, which has 6 links coming out. So this we call it Trinetra A, and it has 600 Gbps full duplex links, and it can have multiple this 3D torus topology. These 6 links can be connected to the near neighbor, and we can have 3D topology, and this can basically scale to thousands of nodes. Now the next technology which is coming up is 200 gigabit with 10 links each. So again here we can have various topologies, including the torus topology. There is another new topology. What we can do is cascaded hypercube topology. With this, the scaling can be up to 10,000 nodes, and is again fully scalable network. We have a very highly complex processor inside this chip, which is basically allowing the offloading of the communication to the hardware, which allows us to have very low latency. The latencies can be in some microseconds. If you use TCP/IP for communication, it is tens of microseconds latency. Here it is less than 1 microsecond latency. So the application can directly write into the communication.
So what is the physical medium of communication? Is optical or direct attached?
So here there are 2 things that are available. One is the copper, other one, these 2 are basically fiber. So depending on the distance, we can connect locally the copper cable, because this is going to be near neighbor. So near neighbor, you can connect the copper, and then when you're going to the little far away, then you need to connect to the fiber. So both options are given. In the earlier generation, we have both options, but it is not feasible to put 10 links in this form factor. So we have gone with 8 links with the copper and 2 links with the fiber, so that we can actually go ahead, go for longer distance. Normally, these topologies for near neighbor communications, so that you don't need a fiber everywhere. Again, one more advantage is it will reduce the power consumption. Cost also is reduced with the copper. And this is going to be available sometime in Q4 23. And we are planning to put a small POC, about 64 nodes, in our next 20 feet of system. Currently, it is FPGA based. We are planning to have ASIC working on this. So same, because this design is completely from scratch, starting from specification to implementation to protocol level, everything is done by C-DAC. Because this kind of networks are proprietary in nature, and the protocols and everything is proprietary. Like InfiniBand is one of the protocols, which is done by Mellanox. Now it is done by NVIDIA. So NVIDIA is the only company who is working on InfiniBand. Similarly, Cray has their own network. So like this, we are also developing our own. There is no standard as such in the market for this particular network. This is the HPC processor. What is we are going to develop, and this is already initiated. which is going to be based on ARM processor. It will have 48 GS core. That is, GS is basically a name for the core which is available from ARM. There are 48 cores in that, in one chip, one chiplet you can say. And the two chiplets together, we are making it 96 core. So there is a die-to-die connectivity between these two chiplets, and they get connected together to make it 96 core in one single package. Now, here I think you can see here, there are multiple memory interfaces available. One is high bandwidth network, a high bandwidth memory, HBM3 is what we are planning to use, and as well as DDR5. Again, this is again latest memory which is going to be available. So both these are going to be available on this CPU, along with PCI Gen 5 for I/O purposes. One more protocol which is called CXL, which is for cache coherent communication, as well as for having cache coherent devices connected to PCI. CXL is also going to be supported. On the software stack, as I told you, phase 1, phase 2 systems are completely based on our own software stack, which is primarily based on open source tools and technologies. We have customized for our own architecture and build this complete stack. Wherever there are components which are not available in the open source, we have put up our own tools. So you can see here, right side, various C-DAC tools are actually put up on this, starting with cluster checker scripts, where it checks the integrity of the cluster, then various cluster utilities, administration tools. Then there are basically this is called C-Chakshu, which is again a resource management tool available. That is again our own thing. CRAME is basically a tool which allows users to remotely use the system with a GUI. Let's say somebody is not very familiar with the normal command line interface, you can utilize the GUI based on that. So here in this stack, we start from operating system, which is again open source Linux based. Then we have middleware and management tools, which allows us to have provisioning of various resources. Then resource management, scheduling, accounting, all those things are part of this. Then on the programming side, you have various libraries which are available. Then visualization tools are available, various development tools are available, programming environments are available. I will not go into these details. So this is the tool which is developed by us. We call it C-Chakshu, because we have 15 systems currently to manage. So we need a centralized monitoring tool where we can monitor all these systems very effectively, and any problems are there, we can actually detect that quickly and then find out the solution. As well as we need to allocate the resources. We need to get the data from this, utilization data from this, so that management can check it out, how the systems are getting utilized, what are the bottlenecks, all those things can be seen from this tool. So as I told you, it is a centralized multi-cluster monitoring. It also does application performance monitoring analysis. So the user can run the application and see how the various nodes are utilized, how the CPU utilization is there, how the communication is happening. It is also again a portal for this. So you can tune the application based on the performance. So as I told you, usage statistics and reporting for management purpose. Live and quick infrastructure visibility via graph, so that we can see whether any problems are there. We have real-time 3D HPC system track view, so that the system admin can quickly go and see where is the problem. Job accounting analysis, again we have even billing also part of this, so that virtual billing can be generated. So that is another thing. So apart from that, we have basically put all the open source application softwares which are customized and ported on this particular architecture what we are supporting on the system. So there are various application tools available, starting from various domains. It starts from bioinformatics, molecular dynamics, various tools. I think whoever is there from the respective domains, they will understand the utility of each of these applications. So the domain users are using these applications for their own research purposes, and these are readily available. So the user don't have to compile and see whether performance are okay or not. We have actually tested the performance, and optimal performance comes whenever these tools are utilized straight away from this system. So apart from applications, we have various other tools which are visualization programs, various dependency libraries, programming models, which includes MPI, OpenMP, OpenACC. Then various frameworks, AI frameworks are there. The DL frameworks, TensorFlow, Keras, PyTorch, and so on. Then we have other tools which are from data sciences. Then container technology is also there. Then Jupyter Hub, again, this is meant for all DL application development. So anybody wants to use this system, because these systems are, even though they are placed at particular host institution, 40% of the compute power is for other users outside the institute where the system is getting placed. So anybody wants to use these systems, they can write to this NSM support at C-DAC.in. What is the compute requirement? And we actually give the access to this users. Again, we are actually giving free to research work and mostly and the students up to certain compute power. So like 1 lakh rupees worth of compute power, we give it for 6 months straight away without asking any questions. But if somebody wants more compute power, then he has to write a proposal to us. And then there is a committee who can actually give this more access. But
what language for writing codes?
Which one?
What language for writing codes?
Writing codes. So I told you, I showed you the earlier diagram. So there are various application environments are available. One is he can straight away start using the application codes which are there already available on the compute, our supercomputers. Other than that, he wants to develop the codes, then there are various languages starting from C, C++, Fortran. He can utilize Python, and there are various libraries which are available to have basically parallel programming, and there are parallel programming environments available. So one has to learn those things to develop the program. So we actually have training programs also how to utilize this computer. So both from domain side as well as from development side. So one can utilize those services from C-DAC. So apart from free usage, we are giving to the industry also and to certain projects where there is money available in the project for compute power. So they can get more priority and basically not only priority, basically assured compute power using this method. And there is a charging model, which is again, as I told you earlier, it is based on only the recovery of the operational cost, not for the capital cost. So with this, I have finished about what is NSM, what we are doing till now. Now we'll go to the basics of what is the HPC architecture. So we have seen that we have developed various components of HPC. So here in this diagram, we can see this side is our compute. So these are servers, various types of servers which will come on the left side. This is the network part, and here there is a storage part. And this is a management part. So all these are connected using the various networks. Okay. Now on the compute part, there are login nodes. So whenever user wants to connect to the system, okay, he comes from the internet or from the closed network through the firewall and gets logged in into this login nodes. Now this login nodes get connected to this compute cluster here, and the jobs can be fired on this complete compute cluster. Now there are various compute nodes, starting with this CPU only compute nodes, where the server will have only CPUs. There is no accelerator in them. Second one is basically high memory nodes. A lot of applications need memory which is very high, example in terabytes. So we have certain nodes with a higher memory, and the scheduling mechanism gives the basically preference to the user to choose what is his requirement, how much memory he wants, what kind of compute resources he wants. So based on that, the job will be scheduled on those particular servers. Third category is basically GPU nodes, where there are different kinds of GPUs are there. In this particular architecture diagram, I put NVIDIA Tesla A100 GPUs. So in our Rudra 1, we have 2 GPUs in each server. So here you can see that 290 servers will be there on this 20 petabyte system. 290 into 2, about 600, 580 GPUs will be there in this particular system. Then we have GPU ready nodes, where I can add on GPUs later whenever it is required. Right now I'm not putting up, but it can be added. So this is the compute part which is there. Second one is basically the communication part. So major primary network is basically InfiniBand network in this case, which is a 100 Gbps InfiniBand NGR network. Gets connect, all this computer getting connected using that, and even the other nodes and storage also gets connected to them. Second network is basically a secondary network. We call it 10G. This is a 10G network. 10G, and this is similar actually. And there is another network is for monitoring the servers, the health of each servers. So this is called IPMI, as well as this can be utilized for shutting down the machine, bringing up the machine and all that. So this is called IPMI network. So like this, there are multiple networks which gets connected. The main network for communication in the application is this InfiniBand network, which is 100 gigabit. Each server will have 100 gigabit connectivity to this network. So, and this is completely non-blocking network. So any server to any server, depending on the network size, there will not be any blockage. So any server to any server, they can communicate at 100 gig. So that is what is the network within that. Now storage is actually a parallel file storage. I'll have one more slide which will talk about the storage in detail. Again, it gets connected to multiple network. These service nodes are mainly for booting the servers. So most of these nodes are remotely booted. There is no hard disk, local hard disk there. Even though there is a local hard disk that is used for scratch space. So people can utilize it for scratch space. So this is the overall typical architecture of any supercomputer as of now. Only thing what changes is what is the network bandwidth here, then what kind of compute you are using, then what kind of storage you are using, what is basically the configuration of each of this. Coming to the performance of this supercomputers, so there are two benchmarks which are there in supercomputing. One is HPL benchmark, which is basically LINPACK benchmark. That you must have heard about top 500 systems. That is based on LINPACK performance. There's another benchmark called HPC benchmark, which is again an application level benchmark where various kernels and applications are put together. And basically, what is the performance of that? So based on that, these are performance. So you can see here, this is slightly older slide. This is not the latest slide. I think maybe 1 year old slide where that time the recon computer from Rican lab has a computer which is called Fugaku, which was actually #1 at that time, which was having HPL performance of 442 petaflop. Now, what I'm showing here is basically what is the performance of this in actual HPC benchmark, which is application level benchmark. So out of 442, people are able to use only 16 petaflop. You can see here, with only 16 petaflop is used for the actual application use for these kernels. So why it is the problem? The problem is basically how much is the memory bandwidth to the CPU. So CPU is there, it is very powerful CPU, but it is not able to get the data from the memory or from the network efficiently. So because of that, there is a choking. So because of that, this performance is going down. So in this particular machine, 0.3 is a bytes per flop. So one flop has 1 byte of basically communication, the memory bandwidth is there. So 0.3 bytes per flop is what is the memory bandwidth there in the first one. Second one has only 0.2. So suddenly you can see the performance drops to only 0.2%. Sorry, 1.5% of the peak. So it is very important to have this byte per flop higher and higher, reaching to the 1 to get the full performance. So the earlier generation K computer was having byte per flop was 0.5, which was having 5.2% of the peak. HPCG benchmark level was about 5.2% of the peak. So it is very efficient because of this ratio. But that is again a problem because once you try to achieve this, a lot of power consumption is going to increase of the system. So people have to actually do some kind of trade-off in when you are scaling to very high level, exaflop or exaflop system or multi-exaflop system. So people are trying to see whether we can have different algorithms which can overcome this problem. But still, one need to try to reach this bytes per flop higher and higher compared to basically what is feasible with the GPU-based system. So the second system is basically a GPU-based system. This is a GPU-based system which is having lesser thing. Even though it is very high throughput HPL benchmark, it is not able to get the performance out of it. So there is a research going on this. That's why in next slide I'll explain about that. What is the memory requirement and what is the memory bandwidth requirement? How people are overcoming that memory bandwidth requirement with the newer technology. So with this introduction, I'll go into the current trends in the technology, various technologies, starting from processor, accelerators, memory technologies, then network, HPC storage, and programming environment. So what are the requirements of HPC processor? One is basically, as I told you just now, is better memory efficiency, memory bandwidth, sorry. Then easy to optimize. The code we need to have very easy to optimize. Basically, any processor now is having vector processing capabilities. So in one cycle, one can actually process multiple bytes in one shot for one operation. Example, you want to do add. It will add different elements up to 512 bytes. Example, if it is 64-bit floating point operation, so such multiple 64-bit can be basically 8 of them can be processed in one single cycle of processor cycle. So that is called vector size. So, but if you increase this 512 to let's say a 1K or 2K or that, the programming is becoming more and more important. How to utilize that vector size to get the performance. So you need to have very ease of programming on this vector engine of the processor. So there is another requirement. Another requirement is basically this, all this should happen at lesser and lesser power. So superior application layer program per power. That is another trend which is coming up because scaling of the systems are becoming bigger and bigger, but power consumption is also increasing. So how do you get the power? Next point is basically better I/O for data access. So as I told you in the previous slide, memory bandwidth is important. So there are different technologies which are coming. One is HBM, and our processor also I showed you that high bandwidth memory is one of the things which is sitting on the chip itself. It is not outside the chip, it is within the chip. So that is one technology which is getting utilized. All GPUs are utilizing. Newer CPUs are coming up with HBM memory on the chip. DDR is another thing which is anyway there. Now next level technologies are coming, DDR5, DDR6. Again, that is increasing the memory bandwidth. Multiple channels of DDRs are coming so that we can get the better and better bandwidth. Then for I/O requirement, PCI Phi is again a network. Basically, it is a I/O network which is connected to the CPU. You can connect various devices there. Example, you can put storage there. You can put communication network there. You can put GPUs there. So these are all required for any CPUs. And the more and more lanes are required for PCI Phi for better I/O. The new technology called CXL is coming up, which is mainly PCI Phi based technology. PCI Phi is the physical layer. CXL is higher level, which allows us to have coherency between the CPU and the devices which are connected to this CXL device. So that when CPUs are accessing this device, or the IO device is accessing this memory, there is a coherency between the two. They don't need to worry about the movement of the data. So that is another technology which is coming up. So all these new processors are coming out with more and more cores within these CPUs. So till now, 128 core processor is also coming. One single chip, you have 128 cores, single chip. So as I told you, our processor is 96 core, like this 128 core processor. And this core count is going up and up, depending on the technology which are coming up. And I already talked about this very high flops, which is again a vector processing, which is again required for HPC. And for AI purposes, you need mixed precision floating point operations, which starts from 16-bit, 8-bit, 16-bit, 32-bit, 64-bit. Because AI doesn't need very high precision floating point unit. So they have 8-bit, also 16-bit also. So where they can have more and more operations in one single cycle by using the same vector engine. Then the processor should have multi-socket support, because again it is when the two processors are connected to on the same system, you get better efficiency compared to connecting through the HPC network. Then power is again very important requirement, because for earlier generation, one exaflop will require 1 gigawatt of power. So you need a one separate station or generation station for operating that system itself. But now it is coming down, and people are targeting about 20 to 40 megawatt of power for exaflop system. So all this is happening by better and better technology in the processor. So this processor also should support GPUs, vector, and application-specific accelerators also. Nowadays they are outside the CPU, but now the newer chips are coming with accelerators are part of the CPU itself. So you have a separate chiplet, which is part of the chip itself, where you have the accelerator for specific applications, which can be a GPU, it can be a FPGA, it can be very application specific accelerator also. So that is again, which is coming up shortly. We will see in 1 or 2 years, CPUs coming out with the accelerator on chip itself, not as a separate accelerator. On the memory side, I think I already covered this. HBM, DDR5, CXL. CXL based memories are also coming up, which is again cache coherent bus. This is mainly for if you have a server with only, let's say, 1 terabyte of memory, you want to expand that memory, then instead of having additional slots on the server, you can connect over this CXL bus. And there again, without any investing anything on the server itself, you just add the memory. So that is again new technology which is coming up on the process side. So this is like a history about the process. So you know that last 1 decade was more than decade actually was for x86 based CPUs. So only AMD and Intel were there in the field, but slowly I think Power, Spark, Vector, they also went away over the period, mainly because of the lack of software ecosystem. But recently from 2018 onwards, various other general purpose processors are come. That is from ARM based architecture, which is coming from Fujitsu, Qualcomm, and NVIDIA. NVIDIA has also come out recently with their own processor, which is ARM based. Again, Ampere is another company who is also coming out with this processor. So this ARM based processors also starting from 50 cores to 128 cores on one single chip. Again, this can be utilized for various applications, but still the ecosystem, software ecosystem is slowly getting developed on ARM based CPUs. From the accelerator point of view, apart from GPUs, there are vector processing engines that are also available from NEC. Then there are some data flow processing accelerators, mainly FPGA based. So people are using this for various specific applications. Again, they are from Xilinx and Intel. Mainly for power consumption point of view, these are basically useful for if somebody has a very specific application, they can utilize this. So as I told you earlier, that the power consumption or the maximum power consumption of these CPUs are going up, and current CPUs are utilizing about 350 watt to 400 watts in one single chip. So cooling and giving that kind of power is becoming challenging. GPUs are having 15 to 60 double precision teraflops as a compute power. And again, they are consuming a lot of power, about 700 plus watts. One single GPU card will consume that kind of power. So these are the trends, what I explained to you earlier on the CPU fronts and various CPUs and GPUs, which are coming up. I didn't specifically mention about what GPUs and CPUs, but there are various things that are happening from various vendors. And I don't want to go into details on that because we don't have enough time for this talk. Next one is on the HPC network. So as I told you, there is a major requirement is the very high bandwidth and very low latency. Otherwise, the applications will not scale, because when the parallel application is running on these supercomputers or these parallel computers, there is a lot of communication between processes happening. The data is getting exchanged between the cores. across this supercomputer. Now this, it is not just the bandwidth which matters, but the latency matters. Overhead of the CPU also matters. So how much CPU you are using for transferring the data, that also matters. So all these three has to be very optimal. So for that, you need to have very specialized. So that's why these HPC networks are designed very specially. So these trends are also going up. In last 15 years, the bandwidth has gone up by 40x, starting from 10 gigabit to now 400 gigabit. So you get 400 gigabit bandwidth between two servers and latency of less than 1 microsecond. So that is the requirement. You have offload of communication on the hardware so that the CPUs are not utilized for communication purpose. Just giving the pointer to the hardware. Okay, you transfer the data from here to here. And it is all done by the network card itself. Then you have a very efficient, low latency, low overhead software stack which is required to utilize this hardware for communication purposes. So now there are other requirements because these networks are getting connected. Tens of thousands of nodes are getting connected using this network. So it has to have resiliency. Any part of the network, if it fails, the complete system should be working fine. So availability, serviceability, all these features has to be there part of this network. Then various topologies has to be supported depending on the requirement. And the scalability also matters. Topology matters for the scalability. So otherwise, the engineering of this system itself will be very difficult. Because there are so many cables coming out of this machine and getting connected to the network. So there are various topologies that are getting utilized: battery, dragonfly, then multi-dimensional torus, and so on. Then again, there are various adaptive routing algorithms are getting developed so that even if there is a congestion on one part of the network, it gets the routing can happen. So such that this congestion is basically avoided by the traffic. Then again, it has to interoperate, and any application working on one network should work as it is on the other. So you need a software stack, a layer, which is basically independent of the network type. So these are various networks which are available: InfiniBand, proprietary networks like C-DAC, Trinetra, or Crane network. So these are the networks which are available in the market. And right side, you can see here there is a low latency software stack. You can see from the application directly the host adapter card can be programmed without any OS coming into picture. So any OS is coming to picture, there is a switching of the task is required, and there the latency will go up. So that's why without having any context switching, the application software can directly write the data or the control data to the adapter so that there is no context switching, but it is there in the TCP/IP kind of network. So which is why overheads are more and latencies are.
So in this, you said that the networks are proprietary, but then how do you ensure interoperability?
Interoperability at the physical level, it is not there. But what happens is on the application level or the OS level, there are only drivers are different. Rest of the stack is same. So that is where.
So there is an industry standard.
Yeah, industry standard for the basically the driver to the higher level. Yes. So with that, you can actually make it interoperable.
Yeah.
That is the way it is possible. So on the storage side, till date only the parallel file systems were utilized, but now there are more and more requirements coming apart from simulation or modeling part of it in the HPC. So apart from modeling, you have a data analytics, Then you have MLDL, that is AI-related applications. So these three types of applications are coming up. So you need different types of storage also. Their requirements are slightly different for each of these applications. So that is why this is a parallel file system requirement. For big data, you need Hadoop, HDFS, or Spark, Apache Spark. Okay, these are the requirements of big data kind of application. And object storage is required for DL and ML type of application. So these are various technologies which are there, which are actually having requirement in any HPC system, because all three types of applications are now converging into one, and people are utilizing it for their own application at various stages of their pipeline. So in the same system, you need to have three types of network storage requirement. So that is where this DIOS is a new open source storage is coming up, which also we are also working on, which will support all these three types of storage semantics. So these applications can utilize a single storage for all these products. And this is again archival purpose. You have a hierarchical storage management, and that is where archival can happen for all these types of storage. Again, the requirements of any HP system is very high bandwidth on the storage side and high IO, that is IO operations, very high number of IO operations per second. And again, the scaling has to be in basically hundreds of petabytes of memory without any scaling and bandwidth issues. And as you increase the storage size, your bandwidth requirements and IOP requirements also go up. So this is the typical storage architecture of cluster, where you have various servers and they have their own local storage available, which is connected using metadata targets. So this is a metadata server. So for file system, you need metadata and actual data, which is called it as an object storage. We have metadata servers and object storage servers, and then corresponding data as part of this. And there's a management related server. And all this is getting connected to the client using very high speed connectivity. Now a single file, which is actually striped across multiple storage servers, can be accessed by multiple clients simultaneously with the whatever throughput what is defined from the storage. So that is the advantage of this parallel file cluster storage architecture. This is the DIOS storage architecture, which uses the flash-based storage. Again, it is very high performance. And as I told you, it has HPC connectivity. Basically, HPC application also can utilize, and data analytics and AI application also can utilize the same storage. So basically, object storage and normal parallel file system both are in one single file system. So I'll not go into details due to timeline. Coming back to now the HPC software stack, as I told you earlier that in earlier stack diagram, we have starting with Linux OS with drivers. Then you have various libraries which are for maths and scientific related applications. Then HPC programming environments, middleware, frameworks, resource management tools. All these are actually required for any HPC systems to work, apart from the availability of commonly used applications. So coming back to the basics of any parallel computer, as I told you that a single program is running across the system with multiple cores in each server. So one need to basically distribute the data to the memory within the memory itself, because there are multiple cores that are utilizing it. then distribute the work to the processors, then organize and synchronize the work and data. So this is the requirement of any parallel program. So application program need to do all this, then only he can scale the application further. Then all this has to be happening with the least resources and most effective way. Then only application can scale across tens of thousands of servers and millions of cores within the system. So for all this, you need various programming environments. So one of the programming environment is basically MPI, which is called Message Passing Interface Library. And MPI plus X means basically message passing is across the nodes, and intra-node is basically within the node, you have a different kind of programming environments. So there are two types. One is inter-node programming models, which basically message passing across the nodes. There are two types of there, MPI and PGAS. These are the two types. One is purely message passing, otherwise partition global address space, where it is like some kind of shared memory. But again, this shared memory concept is realized using underlying message passing only, but the programmer sees as a shared memory system. So intra-node programming model, there are various other models are there. OpenMP is basically, there are threads, multiple threads, they can utilize on the same CPU or same node, you can have multiple threads using this OpenMP kind of model. So these are various models which are available: OpenMP, OpenACC, OpenCL, then SQL. This is again C++ based environment. Focus and Raja, these are again heterogeneous node programming through C++ abstraction. Heterogeneous means there are CPUs and GPUs both can be utilized under this. Then there are proprietary models called CUDA, that is for mainly for NVIDIA GPUs. IP is from AMD GPUs. I'm just giving you this terminology. Maybe if somebody wants to go into the details, he has to go through this. But these are the requirements for any HPC system programmer use. They have to go through this and find out what is the best possible programming environment for make use of this system. So currently, the left side is getting utilized where current HPC system has CPUs and one or two GPUs as accelerators. But the newer system which are going towards exascale, there are multiple accelerators are there in one single node. You can see here right side. CPUs are there, but there are many GPUs and different kinds of accelerators in single chips, including neuromorphic chips. So this is getting complex, more and more complex, with a shared memory across these accelerators and CPUs. So there are newer programming models which are coming up, okay, which are basically this Focus, Raja, SQL, Open API. One API is from Intel, again it is open source. So with this, one can utilize without changing the program, either only CPUs or CPUs plus GPUs. All that can be utilized by not changing the program. So these programming environments are allowing users to select basically while compile time what architecture he wants to use, but without changing the programming pattern. So that is the advantage of these newer technologies which are coming up. And they're slowly taking over so that people can move from one GPU to other GPU or one CPU to other CPU without changing the programs.
So here, this box represents a one chip.
Sorry?
That box in the
Box is basically one server.
one server.
This is one server, okay, and which is having one CPU and there are multiple accelerators. This is a system bus on that, and this is a shared memory across these accelerators. So one server it is. And there are some multiple servers getting connected using a HPC network. So as I told you, there's three types of requirements like HPC, big data analytics, and AI, ML, DL are all required in a single system. So you need to have multi-domain resource manager to have schedule the job of various types, either HPC jobs or Hadoop jobs or AI/ML type of jobs, which are basically TensorFlow, Caffe kind of jobs. So there is a requirement of various tools to have integrated system with all these environments. So this is again newly coming up. Then you need to provision these systems with various requirements, like here bare metal provisioning as well as virtualization is also required in certain cases, where all these containers, OpenStack, AWS, Azure, Google, these are virtualization technologies also need to be integrated in a single system. So this is becoming more and more complex with this newer and newer technology. So this is again one trend on that software stack side. So I have finished about the architecture part. Now, what are the challenges people are facing on moving to the exascale? So main thing is basically people are moving towards the GPUs or the other accelerators like FPGAs and special accelerators. But major challenge is basically ease of programming and availability of applications on these kind of accelerators. So porting the application is becoming challenge. So there are separate programs people are doing it. Even the US also, even though they are developing exascale, those are not general purpose computers. They are meant for very specific applications. They started way back in porting the applications on the various GPUs, and that is how now they are able to utilize those systems properly. Similarly, if we want to go accelerator way, we also need to do that. And to have better efficiency in terms of power, there is a requirement of going towards GPUs, but we can't have from day one the complete GPU system, because we have seen that earlier also various GPU systems are built within the country, but the utilization of those systems are not sufficient. People are using those systems, some of the people are using systems only for CPU. Accelerators are lying idle in many places. So that should not happen. So ease of programming is very important, and the technologies has to be evolved on the software side, and even algorithm has to be ported on this kind of newer systems to utilize those accelerator-based systems. Already talked about the network, where topologies, engineering, and scaling is a major challenge when we are connecting tens of thousands of nodes in exascale system. Data movement is a major challenge, where time taken to move the data from to and from CPU, memory, then network storage is again becoming challenge, and that has to be scaled very well along with the system size. Then second challenge is, as I told you, HPC, data analytics, and AI are actually coming together on single platform. So we need to have a complete platform which will support this. Parallelism has to be exploited by newer programming environments which can scale to millions of CPUs. Then again, management of such a big system is becoming challenge. So we need to develop tools to manage this kind of bigger systems. Reliability is very important, because as you increase the number of components in the system, the MTBF, that is mean time for failure, is actually reducing. So when you are running a program on this kind of exascale system, if it is running for a few days, there is a possibility of at least one component will fail within that time, because so many components are there in the system. So how do you have the resiliency of that, and how the program will continue running without completely rerunning the program? Power consumption is a major issue. Then efficient cooling is another issue, because there are various other technologies are coming, which is liquid cooling, liquid immersion cooling, and so on. Programming models, again, newer programming model has to come, newer tools has to come. And major thing which is coming up is to have newer hardware. You need to develop the newer algorithms which can utilize the current hardware. And the algorithm should actually have lesser and lesser data movements for scaling and less power consumption. That is another challenge. Then when you are running the code on very such large system, debugging becomes a major issue. So there are various tools which are required and various supports are required from the system so that the debuggers can take the data and show it to the user in effective manner. So in summary, HPC architectures are evolving to solve challenges like better power consumption with efficient CPUs and GPUs, efficient data movements, scaling of systems to exascale with higher and higher density, then scaling of applications to exascale with newer programming models, better communication bandwidths, better memory bandwidth and idle. So that is a continuous thing which is happening in. And as I told you, HPC, data analytics and AI together, one single system is again one thing which one need to address to have a very usable, effective system which can be exascale size. So thank you very much. I can share.
Thank you very much. Very extensive treatment of a very complex subject. Obviously, all the hardware, especially the processor, GPUs, the way they are interconnected, and many other issues in terms of the software, the databases, the networking, and I don't know how all this can be kind of integrated well and make sure the whole system works. And you have gone through it step by step. It's a bit mind-boggling to understand from just a user all that happens inside these computers and the amount of time that it takes and the attention to details, and as you said, all that what you listed, even for the challenges to go from HPC to exascale, another big, I think, step forward. We can only just look at and kind of appreciate the efforts of you and your team. Okay, inside that there is a upper limit for our session because there is a class that's going to happen 10 minutes from now. But I think the one has.
I found what is the time limit for Rudra 3.0?
Rudra
3.0, what's the time scale?
We are actually coming out with the next. You are talking about our home-based system. Home-based system will come sometime in 2026. Yeah, when the processor is getting developed, it will take another 2 years at least, 2.5 years to come off.
Yeah, please.
So this was really useful. And one interesting aspect of the NSM is fragmentation. Although you have 64 petaflops, it's fragmented over 15 or systems that individual systems are present by. What is the view in NSM about consolidation, having larger data centers?
Yeah, so one is we have come out with 20 petaflop in the NSM 1.0, the current one, which is going to be national factory. And in NSM 2.0, which we are planning, which is going to be exascale system, one single system, which can be utilized by any of the users from across the country. So that is what is planned. One exaflop. That is what is planned. But there might be some intermediate system also about 200 petaflop. We are just working on the proposal right now.
Yeah, that's.
So, thank you for the nice talk. I just want to ask that we talked about the CPU architectures, about like x86 architecture and RISC architectures like R. I want to know what is the future prospect of RISC-V architecture. So that is like there is a much high going through like in social media and everywhere. People are talking about RISC-V architecture and how it is great and something. So will it change this HPC?
Yeah, RISC-V is open ISA. So people are actually very excited about that, and it is coming up. So server-based, server class RISC-V processors are coming up. So in next 2 years down the line, you will see the RISC-V based server processors. But the ecosystem, software ecosystem is also getting developed across. So I see, I think in another 5 years down the line, you will see RISC-V based HPC systems. And not only CPU, but there will be accelerators also. We are also thinking of working on that.
Okay, I think I see 2 questions from online on Zoom.
Yeah.
Let me ask Professor Vivek Datta to go ahead with this question, and then we'll take up this.
Hello, can you hear me?
Yes, yes.
Yes.
Okay, my question is, what is the typical cost of the 5 petabyte system that you, petaflop system that you mentioned, the best system that you have right now?
See, there is one system which is 5 petaflop, which is the AI-based system, which is GPU accelerator based, which is about 100 crore.
100 crore.
Yeah, 100 crore is only the system cost, but you have other parts like data center, other things that will add to that.
Only the system cost.
Another 20 crore. Maybe you can say 120 crore we should get.
Okay, no, so there's a related question to that, I mean, of course, it would probably depend on the application, but for typical applications, is this cost any smaller than what it would be for a system abroad in the US or Japan? Or similar?
India and Japan, for example.
Okay.
Or similar.
I think this prices are depend on volume. So if somebody wants to build 1 exaflop, definitely he can have much lesser price for the same petaflop. Okay. And another thing is how the technology is developed within the country. So we are actually in the position of bargaining now because we have our own technologies also. So if some country is there who doesn't have anything, their cost will be much higher for the same. So similarly, this thing happens. So Japan might be getting little cheaper than us, possibly, because they have their own technologies, their own things are there. But we also are now in a position that we also bargain with a better price.
Okay. Okay, thank you.
Okay, I think we have one more question from Joshi.
Yeah, thanks very much for this very informative talk. In the context of ease of programming, I just wanted to know if you have a comment on containerization on HPCs. And a second small question is that we have used Param Ganga and Param Seva, 2 of your NSM computers, and we find that Bayesian analysis, Bayesian samplers are very notorious to scale across nodes. So do you have any comments on that in terms of the programming ecosystem?
Okay. So containerization is in HPC is possible, but we have another concept of basically having various applications versions on the system. So we have some environment which actually allows us to have ready applications on this system. So that is one possibility there. Containerization is also possible, but that is mainly in terms of AI and ML is what we are doing right now, but not for HPC. Because once you do the containerization and the virtualization kind of technology, then the HPC systems don't give that kind of hope. The second question, what is the question? I just
Yeah, second was related to Bayesian samplers, you know, MCMC and dynasty kind of the hierarchical samplers. These are very difficult to parallelize across the nodes. So I'm wondering whether anyone in C-DAC has sort of attempted that. If so, we will be very much interested because we are finding trouble in Param Seva and Param Ganga to do that.
Okay, okay. So I am not aware of that. Maybe you can connect me. I will connect you to the proper person in this.
Yeah. Okay, thanks.
Thank you. Thank you.
I think this last thing.
Yeah, so it's great to see that real You are developing the road processor, the phone processor. Can you please say a little bit more about that? Which technology, fabrication technology?
This is going to be 5 nanometer technology.
Which companies, I think, or few companies?
That is TSMC
Yes,
foundry, yeah.
and you are using this ARM cores,
Yes.
cores.
Yeah,
So is it that in the public domain or you have to pay license fee?
we have to pay license. We have to pay license.
And how does that come? So Apple is also using this ARM cores now in their chips.
Yes.
So is it the same cores or they are?
Apple may be using little different because they are not having HPC class processor. They are having, I think, maybe for their workstation others. But there are other companies like NVIDIA is coming out with the Grace CPU, which is ARM based. Again, they are using similar core from ARM. So this core is available in some source code form to us. We can actually port it on various technologies. So that is where we are working. Thank you.
Okay, I'm sure there will be more questions on the post colloquium T, but since we are running short of time, we would like to thank Sanjay for his fantastic talk today. One thing I think I couldn't take you enough around for the TFR art collection and whatever you have seen, all that are in this book. So we'd like to give you this to have a look at what's in it. And the forum in which you spoke, instantly also completed 40 years of it. We have a moment of review to take back. Thank you once again. Yeah, please join for a cup of tea in the rest canteen.